Kia ora koutou, ko Douglas Walker, tōku ingoa. I'm here tonight with Andrew Sargent. Andrew is a teacher at Tukura, and he looks after physics over there. So he's going to run us through the level 3 external for mechanics tonight, and then we're going to catch up with him again tomorrow night for the waves and electricity papers. So if you haven't been to one of these before, if you've got any questions, please put them in the chat, and I'll either interrupt Andrew as he's going and ask him those questions if they're time sensitive. Otherwise, I might collate them until towards the end. And we're very grateful to the support of Study It for helping these webinars to happen. And if you've got time, head over to Study It. It's a great forum where you can ask all your questions relating to your externals and internals. And they've got a little survey up to help improve Study It at the moment. It'll only take a couple of minutes, and if you could do that, that'd be great. All right, thank you very much, Andrew. It's great to have you with us tonight. I'll hand over to you now.
Kia ora tātou. Right, so I'll quickly just share my screen. Probably that one there. And how do I minimize that? Nope, that's not what I want. There we go. Right, you can
want your face to show while you were running.
I mean, doesn't really matter. I'll just tuck down the corner because it's out of the way. Should be fine. Right, so I have chucked this hyperlink in the chat for everyone to follow through if they want. I'm not going to make a big screen, but I've got some really good resources. So there's my channel, which has a whole lot of videos. I've got the last 5 or 6 years, plus scholarship as well. There's Mr. Wilbley, who's got last 2 years. His are probably better than mine because they look nicer. He's probably better explaining them. I've got the physics folder as well. So inside this folder, you can find all the past exams. It's like all the way down to 2004. If you try and search on the NCEA site, you might only find down to 2009, and it's not organized categorically and named real easily as well. I have a simulator site here that I've hyperlinked in, which is an awesome site. It's got absolutely everything for level 3 and level 2 physics. For electricity. Oh no, yeah, maybe not. So for the circuit, so the second simulator down, which is a circuit simulator, I use exclusively for the electricity topic. It is phenomenal for explaining AC circuits. But I'll be going over that tomorrow night. And then I've got the link to Physics Realm, which you can just go to their website and have a look yourself. So mechanics is split into 4 semi-distinct sections. Translational motion is sort of out there on its own. It's sort of, there's no usually full questions of translational motion. However, in this exam, I'm going to go through the 2014 exam today. For those who want to know, there is one question at the end which is pretty much entirely translational motion. Circular motion, gravity, so it's like Kepler's law, where you equate the centripetal force formula to the gravitational formula. That's really common. Rotating systems, also really common. I mean, yeah, anyway, so I'll go through each one individually. So I have categorized all the last 5-6 years, down to 2014, when these questions have occurred. So in the 2014 exam, question 3, the whole entire question 3 was a translational motion question, and so on and so forth. Circular motion and gravity. Obviously, it's quite a common question because it's pretty much come up in every single exam. 2020 was the whole of question 1. Rotating systems. So this comes under angular momentum, the rotational kinematic equations, if that makes any sense. So there's a bit of a pattern. 2016, 17, 18, 19, 20. Every single time it's in question 2. My bet's going to be 2021 is going to be question 2 as well, but hey, it might not be. Who knows? So oscillating systems, it's commonly known as simple harmonic motion. It's typically always been question 3. I don't know why it's question 3. It's the last chapter of the mechanics, most mechanics textbooks. So yeah, it's a very common question. Things that you should know are the definitions of simple harmonic motion. So like what defines simple harmonic motion, and that is that the force is linearly proportional to the negative of the displacement. If you want an example of that, you can just look up. Not last year, so the 2019 exam, question 3A, I think asked for the definition of simple harmonic motion. I think the 2018 3A as well asked for it in a different style. It asked for it, but it still asked for like this for the definition. Right, so I will move on from here. I put this at the top of the chat, so you can open this up and go through these if you want. But instead, I thought I'd work through the 2014 exam paper. Right, so we have, what do we have? The universal gravitational constant. It's a rotational motion question, but really it kind of is, but it kind of isn't. So we've got the radius of the sun is 6.9 times 10 to the 8, or 6.96 times 10 to the 8. It rotates at a rate of 14.7 degrees per day. Show that the period of rotation, this video is going to be saved and uploaded later. Show the period of rotation of a particle located at the equator of the sun is 2.12 times 10 to the 6. So this question sort of wants you to know, you sort of need to know what the definition of period is. And the definition of period is, so like T, capital T for period, is equal to cycles. So cycles, I'm not going to spell that all right, per second. So how many, hold on. Seconds, let's round backwards. It should be seconds per cycle. This is probably the most easiest confusing thing I ever have to teach because it's so simple, it's complicated. So it's, I'll just quickly delete that. It is going to work. Because frequency is cycles per second, so period, seconds per cycle. Right. So is equal to seconds per cycle. Right. So how many seconds do we have? Well, we have a whole day because it rotates of 14.7 degrees per day. So we're just going to turn that number into seconds. So we're going to go 24 times 60 times 60 because we're just going to have the units over the units. And then we're going to ask ourselves, well, it's 14.7 degrees. One whole cycle would be 360 degrees. So we'll just turn that into the fraction of the cycle because this time is also the fraction of the cycle as well. So we're going to go 14.7. I'll just put the slash for divided by 360. Put brackets around that. And then we'll quickly do that in our calculator. So 24 times 60 times 60 divided by, I chuck brackets here, 14.7 over 360 bracket equals. And that gives us, how many dots is that? 1, 2, that's 3, that's 6. It's 2.115. So 115, and we probably could have rounded that to 6, couldn't we have? To 6, and that is times 10 to the 6. So times 10 to the positive 6 seconds. And because this is a show question, you kind of do have to have a formula. So for show questions, you have to have a formula, then a substitution, then the answer. So here I've got T equals seconds per cycle. I put in the seconds, I put in the fraction of the cycle that those seconds occurred in. And then because this here is 3SF, this is 3SF, and then I give my final answer down here is, I just give it as what I've given it to you. So 2.12 times 10 to the 6 seconds. And I'll just quickly scroll down. Right, so calculate the linear speed of a particle at the sun's equator. So this is where you can go to the formula sheet. I don't know if there's a formula sheet. You might have to memorize it. Here it is right here. So here is the formula that we're looking for. And we're also going to be looking for Did they give it to you? Omega equals 2 pi f. There they do. They're right. Give it to you right here. So those two formulas here, we're going to put the angular velocity in for the the angular velocity into that formula. So we're essentially going to have v is equal to, instead of omega, would be r2 pi f. But we don't have the frequency, we've got the period. So the period is the inverse of the frequency. So that is just going to be equal to 2 pi divided by the period. And I'll quickly do this on the calculator. So we've got the period or the radius. So let's clear this, 6.96. That's e to the 8, and that is going to be times 2 shift pi, and that equals, and we'll divide that by, we should really do the unrounded number. So it should be 2.1159. I just remember it was 2.1159. E to the 6. Yep, and that gives us 2,606 point, what do we got? 77. 77. Probably just round. I'll put check in there, and there's going to be meters per second because I want to round later. So now I want to round at the very end. I do my final rounded answer is round this to 3 SF, so it is going to be 2,070 meters per second. There we go. Right, so the takeaway from this question is to know the definition of things. So know that period is seconds per cycle. Well, know that frequency is cycles per second, and then you can just flip that idea around. So it's always easier just to know that frequency is just cycles per second. So period is the inverse of that. So you flip that idea around, so you get seconds per cycle, and then you just put it in the seconds, get the cycle. And this applies to a lot. This method of solving problems applies for a lot of things. Right, so I'm not going to write out these long questions. I'm going to talk my way through them. So gravity may cause a rotating inner core of the sun to collapse much down to a much smaller radius. Explain how this will affect the angular speed of the inner core. So these style of questions are conservation of angular momentum questions crossed over with rotational inertia. So there's been a change in rotational inertia, which has caused a change in angular velocity. So first things first, you write the general angular momentum formula. So a lot of students, I'll just write it out first. A lot of students in VR think this is the general formula, the angular momentum formula. It's not. This is like MVR only occurs when you have the mass distributed at the very tip of the radius. The general form is the angular momentum is equal to the rotational inertia multiplied by the angular velocity. And then, so that's like the first idea. And we have the second idea is the rotational inertia is equal to, I'm going to put some constant K. So we're going to put some constant K times m squared. The reason I put the constant K is because in level 3, you're not given all the fractions for different shapes. So different shapes have different rotational inertia. A solid cylinder has objectively less rotational inertia than a hollow cylinder, for everything else being equal. So like same mass, same radius, but just different mass distribution. So you put that value K in. You don't have to, but it can keep track of things. For example, what exam was it? I think the 2015 question 3, where they have a rotating cat. They have the front legs of the cat spinning one way, the back legs of the cat spinning the other way. If you had K as a placeholder and you carried it all the way through, it cancels itself out, and you didn't actually need to know what the fraction, what that fraction was. And this occurs a lot. So let's just answer the question. The radius has decreased. So the radius has decreased, which means the angular, the rotational inertia has decreased. There are no external torques because it doesn't appear to be any. This says it's a rotating inner core collapses. So it's the inner core of the sun, which is an internal structural thing. So there's no external torques. Thus, angular momentum is conserved. Common misconception that students put is they say angular momentum is conserved if there's no external forces, which is not true. It's only if there's no external torques. An example of this is a frisbee. If you throw a frisbee, the active, like let's say you spin it up and then you whack it, it'll keep on spinning at the same rate if you whack it like straight off the back of it, because you're not speeding it up or slowing it down. So it's only if the force is applied with some perpendicular component to the radius. So the angular momentum is conserved. So this, you should never do these arrows. You should say the actual words. I'm just doing it for like visual effect. So angular rotational inertia has decreased, which means the angular velocity will increase. And this is usually an excellence question. And I've got the answer scheme. Is it an excellence question? Yeah, it is an excellence question. Just about every year it's an excellence question. I think in the 2018 or 18 exam, they had a satellite with little lever arms, and the satellite was rotating, and the lever arms retracted in. Same style of question. You also get decrease of the radius, decrease of the effective mass distribution, which means the rotational inertia decreases, and it speeds up. Just a little, like an extra tidbit is angular. Oh wait, hold on. The rotational energy of the sun will increase, and also let's just go back to the satellite. When the lever arms pull the thing in and it speeds up, because I'll just chuck the formula here. EK, I know I'm riffing, but this applies to a lot of questions. EK equals half I omega squared. Because the angular velocity is squared, if you decrease the rotational inertia, the angular velocity increases like linearly, but because the angular velocity is squared in terms of energy, the energy always increases for things that like reduce their radius. And the reason why that happens is because work is done to pull those lever arms in. If you ever spin around and pull your arms in, you're applying a force over a distance because you've got that tension force, you're increasing it. So that's where the energy comes from. In terms of the sun, it's the gravitational potential energy is lost because all that matter has fallen closer towards the sun. So it's gravitational potential energy that's getting lost. Right, that's probably enough for that question. Right, what do we got? Next question. Mass of Mercury is 3.3 times 10 to the 23, so it's a planet. Cool beans. Mercury is a period of 5.067 times 10 to the 6. Show that a satellite needs to be positioned 2.43 times 10 to the 8 from the center of Mercury so that it remains stationary from the point of view of the observer. So this is what's called a geosynchronous satellite or geostationary satellite. This is an application of Kepler's law. So the best example of this question is the 2015 question 1D. Was the best example where it had, so it's pretty similar. This is a quite common question. So we start off with so that it remains stationary. So what holds the satellite in place? Well, that's gravity. So we're going to have Fg, and it is okay. So it's not given away in the question, but it's circulating the planet. So it's held in point, and as the planet spins, the what do you call it? The satellite is spinning with it. So we want the period of the satellite to be the same period of the planet. So that's like the crux of this question. But it's sort of, sometimes it's assumed, but it's not really picked up on. So we have a center pointing force, which is gravity. So it's going to be, we need to use, it's FC. So write this out slightly larger. The gravitational formula is big G, big M, little m over R squared. And the centripetal force formula is mv squared over r. And what we're trying to find, needs to be positioned that from the center so that it remains stationary from the point of view of the observer of the planet. So we're trying to show that this is true. So this is r. This is the radius from the center of mass to the satellite. So what we want to do is rearrange this equation for r. So probably what we want to do is we'll divide both sides by the smaller mass, cancel that out. We'll times both sides by r, cancel that out. And I'll just put a dash here. So we're going to have big G, big M over r. And that would be equal to v squared, but we don't have the velocity. However, we do have the period, and we do have like the distance. So we can break down velocity. We'll break down velocity into distance over time, and that's going to be squared because it's velocity squared. And I'll move this down here. So we're going to have big G, big M over R, and that is equal to, so the distance around, like the satellite is taking. Yeah, I'm doing waves and electricity tomorrow night. I'm doing electricity at 6 o'clock, 6 to 7, waves from 7 to 8. So the distance the satellite goes round is a circle, so that's 2 pi r. So we're going to have 2 pi r, and that's over the period, or just the time it takes to get all the way around. So that is t. So for those that are familiar with this question, this is a derivation of Kepler's law that shows that t squared, the period squared, is proportional to the radius cubed. It's the same derivation. That's squared, and now we'll just expand this out. So this is equal to 4 pi squared r squared over t squared. And then I'll times both sides by r, and I'll move this r here up to the other side. So, and I'll do that. So yeah, Gm is equal to 4 pi squared r cubed. And I would be divided by t squared because it's underneath, but I'm going to multiply by both sides by t squared and put it over here. T squared. And now I'll divide both sides by 4 pi squared. So if you're wondering where the 4 came from, it's because I squared 2. Sometimes kids don't pick that up. So I'll divide this by 4 pi squared. And now you can see all I need to do is cube root both sides. So essentially I get, I'll just rub this r out and I'll cube root both sides. Rub that out. So cube root, and that equals r. Right, so I might do this on my calculator actually, just so when you're doing this question, I'm sure you know how to use a calculator, but I'll just go through like little bits on how to do it, I suppose, efficiently. So we got period is 5.067, whoops, 5.067 e to the 6 squared times, what's the gravitational constant? I can never remember. I'm pretty sure it's 6 point something. Oh, what is it, gravitational? 6.67 times 10 to the negative 11. 6.67 e to the negative 11. Jump back into here. And the mass of the planet is, what is the mass of the planet? 3.3 e to the 23 divided by bracket 4 times shift pi squared bracket, and I'll hit equal on that, and then on a where's the cube root? There it is. So shift, no, that's not what I want. Oh no, equals, and then when I go 3 cubed shift answer. Hey, and we got the answer. And I'll quickly just move up, scroll down to messages. Cool. So we're going to have, this is equal to, I'll just count the numbers. It's 3, another 3, that's 6, 7, 8, 2. So it's 2.428, that'll do, times 10 to the 8, and it's a radius, so it's meters. And then down the bottom, we chuck in our actual radius. So we have r is equal to, round this up to 3SF, so it's 2.43. And it's done it there. So 2.43 times 10 to the 8 meters. Cool. Next question. Space probe spins around on axis shown below. An instrument comes loose from the probe. Explain why this loss of mass has no effect on the angular speed of the space probe. So going back to the conservation of angular momentum is conserved. In other words, it doesn't change if no external torques have been applied. Or this probably won't explain this, but let's think of a better example. Yeah, okay, I've got a better example. Angular acceleration is equal to, let's jump into the formula sheet. So always get it. Angular acceleration, jump up here. No, it's not that. It's torque over inertia, pretty sure. Torque over inertia. Yeah, it is. So torque over inertia. Now, there has been no torque applied in this situation. It's just detached. It's just come off. So if there's been no torque applied, there's no angular acceleration, which means there's going to be no change in speed. And then you can say, well, why? Well, that pretty much just answers the question. There's another way to answer it, is because when the piece of mass comes off, it leaves with angular momentum. So the angular momentum drops, rotational inertia drops, so the angular velocity doesn't change at all. So we've got, here's our angular momentum equals I omega. The mass drops, but the angular momentum drops as well, because that mass took off with a bit of angular momentum when it left. But because there was no torque applied, there's going to be no angular acceleration, so it won't speed up or slow down. Right. Cool, next question. We had a pendulum set up. You got a whole lot of details. Calculate the time it takes for a pendulum to swing from one side to the other. So it's a pendulum. We can assume it's a pendulum, so we can use a pendulum formula. So the period is equal to 2. Oh, that should be a 2 pi square root L over G. And the period, or the definition of a period, is seconds per cycle. So this would tell us the whole cycle. So from one side all the way to the other and back again, because it's one repetition of the, I don't know, of like the shape. I don't know. It's just one repetition of the thing. So in that case, we just have to put the numbers in and then divide by 2, because it's only from one side to the other, because it's half a cycle. So we can probably just quickly do that now. What's the length? Length of the chord is 1.55, isn't it? 1.55 divided by 9.81, because we're level 3 students. We use 3SF, equals shift square root shift answer, equals times 2 shift pi, equals divided by 2, because it's half a cycle. So I'll write this is actually equal to 2.49 75, I suppose, seconds. Half cycle equals, equals to 1.24. That should be 248 seconds, and then we're going to round this up. So just checking time down here is equal to 1.25 seconds. There we go. Let me just quickly check my notes. Made calculator errors. Pretty sure I haven't. No, I haven't. Sweet. Next question. Explain how the forces acting on the bob change the bob's speed as it travels from release to the center. So I suppose this actually does come into the definition of simple harmonic motion. So simple harmonic motion occurs when there's a restoring force that's linearly proportional to the displacement. So this is why pendulums have this small angle approximation. It's because if you start going past about 10 degrees, the acceleration increases exponentially. Increases not linearly. I can't remember straight off the top of my head. You can derive it. The derivations on YouTube typically involve Lagrangians. So it's not very accessible for it is kind of accessible for a high school student, or calculus. There are some really old textbooks. If you find like old textbooks from the 1970s, they have really good derivations for like a simple pendulum. There's probably some like in the back of some classroom if you're wondering. Anyway, right. So at the top, it's got tension force. So I'm just going to talk it through. I'm not actually going to write it out. And then you have the gravitational force. And then these two components add together to create a force like so. You can just do vector addition. So at either side, they add together to create a restoring force, which brings the bob back into equilibrium. So that restoring force accelerates the bob up. When it hits the center, so here's the bob at the center, you have the tension force, which is going to be larger than the gravitational force. I'm just going to draw straight over my thing. Why is it larger? It's because it's going around in a circle. So it's a circular, it's changing direction. So it's a circular motion, it's a centripetal force. It's going to be larger because it's changing direction. But it's not going to be speeding up because the net force is vertical and the velocity is to the side. So it's not going to change the speed whatsoever. It's simply going to change its direction, which is upwards because it's going to be going up the ramp. And then at the top on the far side, it's just going to be symmetrically the opposite. And another way to reframe this question is on a YouTube channel called Bruce Yearney. He has, 3 or 4 years ago, you can make a half pipe and then you get like a bowling ball, not a bowling ball, a pool cue ball, and you can roll it back and forth, and it's exactly the same as a pendulum. Everything's the same, and then you can think of it differently in terms of, if you remember level 2 where you have like a car parked on a hill, or not a car rolling down a hill, I should say, the resultant force is actually down the hill. It's not horizontal. So that pretty much answers that question. Hopefully, there's no questions in the chat. So that
I wonder if we could just address the issue of big T versus little t for period and time.
Oh yeah, I probably should have. That's just me being lazy. So this should really be, good point. This should be little t, because big T represents the full cycle, little t represents just like a period, like amount of time. Good catch on that one. Right, what do we get next? So bob is released again in such a way that it swings in a horizontal circular path with a radius of 0.29 meters as a conical pendulum. So I know the Bozeman textbook has a derivation for the conical pendulum. I can't say the same about the other textbooks off the top of my head. I'm not sure if they do or not. It's a scholarship-ish concept, but not really. So by first calculating the size of the angle that the chord makes with the vertical, show that the tension force in the chord is 18 newtons. So a little bit sneaky, they've put this radius on this side, but really this makes just the same, that should be a straight line, same triangle. We are trying to find out this angle here. This is the hypotenuse, this is the opposite. We're going to be using sine. So we need to find the angle, and then we get the achieve mark. But we're going to need to find the angle, so we can do some free body diagram of the situation, and then work backwards from there. So we all, like the way I like do trigonometry, I always write out sine theta is equal to the opposite over the hypotenuse, and then I substitute some things in. So sine inverse, I'll just set a sine inverse of both sides, is equal to the opposite, which is the opposite. It's 0.29, and the hypotenuse is 1.55. 55, and I want the angle in degrees just because it's just more visually appealing. I don't always work in radians. I swap around. So I'll just check this down here. And I know shift setup to change my calculator 2 degrees. It doesn't really matter. If you work in radians the whole time, it's fine. Sometimes it can throw you off. Shift sine bracket 0.29 divided by 1.55 bracket equals 10.783 degrees. Notice I'm not rounding until the very end. Only round your final answer. Because if you start rounding halfway through, it can throw your answer off. Right, now we have so we're trying to show the tension force is 18 newtons. So we have the gravitational force, which is just going to be mg. That's just mass times gravity. We have a tension force that's some value, and we know that it's going round in a circle. So we know that the vertical component of this tension force is equal to the vertical component of gravity because it's not going up or down. So that's how you know that the tension force is larger than gravity. And from there, you can just do a quick triangle, so we can go up the tension force. I'm just being a little bit pedantic by making it a bit more of an angle than it should be. Down the gravitational force, that is Fg, this is Ft, and this is a net force. So I'll put a dotted line. This is the sum of those two forces. It's an unbalanced force, and that's what makes it go around in a circle. And because it's going around in a circle, it's a circular, it's centripetal, center pointing. So we'll call it Fc. Notice I'm very careful about how I say Fc because a lot of kids just call it centripetal force without realizing it is the horizontal component of the tension force which makes it go around in a circle, not centripetal force. Centripetal forces is just the name. Anyway, maybe pedantic. So this angle is theta. I want to find the tension force, so I have what do I have? Do I need to? Yeah, just the tension force. I have the adjacent, I have the hypotenuse. I'm going to use cos. So cos theta is equal to the adjacent over the hypotenuse. I'm trying to find the hypotenuse. So I'm going to have the hypotenuse is equal to the adjacent over cos theta. And that is going to be equal to the adjacent is just the gravitational force. So it's mg over cos theta, which is going to be equal to, just do this one. No, do I squeeze it in down here? What's the mass? What is the mass? 1.8 kilograms. 1.8 times 9.81 divided by cos 10.7, that should be bracket, 10.783. There we go, and that is going to be equal to, so I'll quickly just go 1.8 times 9.81 divided by cos bracket shift answer, because I saved that previous answer, bracket should be equal to 18. 17.97, close enough to 18. That is 18 enough for me, and that is newtons. So down here, we're going to have Ft is equal to 18.0 newtons. Just give the ones that they used. So this question here is identical to previous one, but you have to check the PowerPoint because I can't remember straight off the top of my head. It's like maybe it might be 2018. Right, and the last question, calculate calculate the speed of the mass that must have been given when released in order to attain a horizontal circular path at radius 0.29 meters. So from there, you can do both of these questions independently. So let's just quickly sketch up my triangle again. That's Ft, this is Fg, and this is Fc. This is the angle theta. I'm going to use tan because I want to use the opposite and the adjacent. Tan theta is equal to the opposite over the adjacent. The opposite is Fc, the centripetal force. The adjacent is mg, because gravity. And that is equal to mv squared over mg. So we can see that we can cancel out some masses. And, oh, whoops, there should be, what am I doing? mv squared over r. And we can see that we can, I know what I've done, skip a few steps. There should be mv squared over r divided by mg. But what I'll do is I'll move the mg over to the far side because that's normally how it's done in textbooks. So mg tan theta is equal to mv squared over r. Yeah, so this derivation is actually done in the Bowersman textbook. Divide both sides by the mass, like so. Move r over to the far side, so you get v squared is equal to rg tan theta, and then we can see that if we rub out we can square root both sides, so we get that there. Some kids choose to memorize this formula just because it's quite often just given as that and just told to memorize it. But it's easy just to work it out from just using trigonometry. it's easy enough to work it out using trigonometry, as long as you draw your triangles and then label them. And from there, we can probably calculate it out. What's the radius of the circle? 0.29, I'm pretty sure. Yeah, I'll do it. Pretty sure it's 0.29. I better check. Oh, too far. Yeah, 0.29. So 0.29 times 9.81 times 10.7. Pretty sure. And 0.29, 9.81, 10.7. Shift answer. And better check that's right. Is that right? Yeah, it totally is. So that equals 0.733 meters per second. There should be a point there. And the answers is rounded up to 2 SF, but really you should give it to 3 SF. So it should be V is equal to, I better double check, I've given everything to 3 SF. They might have given the, 3. Okay, everything's to 3. So this should really be the 3 significant figures. It should be 0.733 meters per second. Cool. Next question. So this is not a very common question. I thought I'd go through it just because maybe this year it's due for a question like this here. Didn't have it last year. They had it the year before. That was a lot of me sort of gambling. So we got two discs, A and B, attached together like cord. Disc slides across frictionless surface. Disc A has a mass of that. B has a mass of 0.684. This one, B is stationary. Show that the speed of the center of mass is 0.52 meters per second. So you're not given this formula, but you're given the general center of mass formula, which is, where is it? Where's center mass? Here it is here. Here's the center of mass formula, and basically states the sum of the moments, which is mass times the distance, divided by the sum of the masses is equal to the center of mass. So if you take the derivative, so I assume that a lot of people here have done calculus and know what derivatives are. If you don't, if you just drop down from distance to velocity, you get a velocity answer. So if you use momentum, so mass times velocity plus mass times velocity divided by the sum of the masses, will cancel out all the masses and just give you a velocity. So you're adding up all the momentums, because momentums are a vector. You're adding them all up, assuming they're all in the same plane. That's why you've got like x1, x2. So you're adding all the momentums in the same plane, and that'll give you the sum of the momentum in that plane. So we'll quickly do that. So we're going to have, I'll call this VCOM. VCOM is equal to M1V1 plus M2V2 divided by M1 plus M2. And that's going to be pretty easy. We've got these times together equals something. This times together equals nothing, because it's 0.684 times 0, because it's not moving, equals 0. So we have 0.517 times, or 1.21, divided by 0.517 plus 0.684. And I'll do the work. I'll quickly do this on my calculator. 0.517 times, 0.517 times 1.21 divided by bracket sum of 0.517 plus 0.684 bracket. Cool. Show the speed of the center of mass is that. What have I done wrong? Well, out of those 0.517, 0.517. That seems slightly off. Huh. Close, but not exactly. What have I done wrong? Can we use conservation momentum to solve this question? This is essentially what it is. This is, it's essentially conservation momentum. What? I'm going to quickly do 0.517, 0.517, 1.21. I'm going to chuck some extra brackets in here somewhere. I'm losing my mind.
Go back and check your 0.654 on the calculator. Should be 0.6.
684. There you go. Thank you. Delete. Losing my mind. There you go. Simple numbers. Yeah. Thank you for that. 0.5208 equals. This is going to be V com. 0.521. Cool. Yeah, people picked up in the chat. Good spotting. Right. Disc collide. After the collision, they are moving at right angles to each other. Disc A receives an impulse of 0.25 newton seconds. Show that the speed of disc B after the collision is that. Right. So this is going to, this divulges into the definition of what impulse is. So impulse is change momentum, but really it's exchange of momentum. So if there's an impulse between two things, one loses the exact momentum that the other gains, assuming conservation momentum, assuming you got no external forces, so on and so forth. So what this is telling us is B wasn't moving to begin with, so it had no momentum. It had an impulse or a change of momentum of that. So we can quickly, change of momentum for B is equal to the mass isn't changed, so we're fine with that. Mass, because it's not changing, times change in velocity. We know the change in momentum of B. I'll write it out fully. Momentum final of B minus momentum initial of B is equal to the change in momentum of B. That's meant to be like little subscript B. I'm trying to kind of neat and tidy. The initial momentum of B was 0. So the final momentum of B is equal to the change in momentum or the impulse given, which you can sort of see that, the change in momentum, so the impulse of B divided by the mass is going to equal the velocity. So that's going to be equal to the 0.25. So this is where they've thrown you off. They've used the alternative units for momentum, which is force times time, whereas they could have just used kg meters per second. Where if they gave you kg meters per second, you go, that kind of makes sense. It's gained that amount, but because they used the force times time, it's deliberately done. I don't know if it's deliberately done, but I would assume that's what I'd do. If I was going to write a question like this, I'd deliberately chuck that in there just to throw kids off, just because I'm mean like that. Right, so 0.250 divided by the mass of B is 0.684, and I really hope I get this right. 0.25 divided by 0.684 equals, there we go, 0.365. I'm not going to write the rest, meters per second. And then explain your reasoning. It's because the momentum is an exchange. So A loses that amount, B gains that amount. Right, determine the size of the momentum of disc A after collision. I'll quickly do that. So A is going to be, what was A initially? It's going to be, it's the same approach. So A is losing that amount of momentum. So we'll quickly write out momentum final of A minus momentum initial of A is equal to the change in momentum, or the momentum. It's just the change in momentum of A. And this is where, I suppose, the physics applies. A collided with something, so it's slowing down, so it's losing momentum. So in other words, this is like a positive number. Hold on, wait. Final initial. This has to be less than that. This is a negative number. It should be a negative sign because we know the final has to be less than the initial. So we're trying to find the size. We're trying to find the final momentum. So we're going to have, it's going to be P final of A, and this is plus. This is minus on this side. So it's going to be plus on the other side is equal to negative change momentum of A plus the initial momentum of A. And then from there, you can see that's just going to be 0.25 minus, what was the initial momentum of A? What was this mass times velocity? It is 1.21 times 0.517. So 1.21 times 0.517. And that should give us 0.25 minus bracket, how much time? 10 minutes left. 1.21 times 0.517 bracket, and that gives us negative 0.3755. Is that what I wanted to find? Hopefully. Where did I check that? What have I done wrong? Oh, that's what I've done wrong. I have to delete this because I just realized just A. Okay. And this is where I should use vector. So when I did that before, I was doing the impulse, but I realized I have to use the vectors. So this is where I'll quickly sketch it up. The initial momentum of A is this is the initial momentum of A, and then this is equal to the final momentum of A and B. So in other words, this is equal to the momentum of A, and that's a vector. We'll just call this momentum of A, and the momentum of B. It kind of looks like it goes down like that. And these two are equal to each other. So in other words, this here is the initial momentum of A, and that's a right angle, and this is momentum of B. And now you can see this is Pythagoras. So this is the same as a 2018 question, I think it's 2, question 18 2. 2B maybe, or 2019 2B. So it's quite a common-ish question. Easy to make a mistake if you don't realize they're going at right angles to each other, or if they break away. I think this is a question I'd written notes on that I'd forgotten to go back to. So now we can see it's going to be Pythagoras. I'll go down and I'll just write it out. So we have the initial momentum of A squared is equal to the final momentum of A. So I'm doing big P's just so it's easier because I can't do tiny wee subscripts.
The initial momentum of A, or is it the initial momentum of the system?
Wow, A is the system. You're right, I should put the system, but I couldn't quite decide whether I do the system or A, because A is the system to begin with. But you're right, it probably should be the system, but it makes probably the math maybe a little bit easier. Maybe, I don't know. Plus the momentum of final momentum of B squared. And now I just need to rearrange. So the initial momentum of A squared minus the final momentum of B squared, and then I square root this. And this equals the final momentum of A. There we go. And then how much time have I got? 0.54. I'll quickly. No, I'm not going to do the calculation because I'm going to do some explaining. If you go back up to here, if you didn't know, so if this wasn't a right angle, so let's assume this triangle was not a right angle, and it was something like this, and it was something like that, and then this is B, and this is A, and you knew, like normally they'll give you something like this, and then this angle here might not be a right angle. So what you do is you split this up into two triangles, and they normally will give you one of the vertical components of velocity for A or B. And if they give you the vertical component of velocity for A or B, then you have that vertical component of momentum, because A and B, initially there was no vertical component of momentum. So finally, the final vertical component of momentum sums to 0. So in other words, A's vertical component of momentum is equal to B's vertical component of momentum downwards, and they add to 0 because the initial vertical component of momentum was 0. And then from there you work backwards. You find this length here, and then from the angles you can then find, from the angles you'll be able to find all the components of the triangle, because they might give you, they'll probably give you some angle, and if they don't give you the angle, then you better find that angle from the other components, if that makes sense. So maybe they gave you the 0.57 and they gave you one of the speeds. So this is the one, like this situation is a one situation where you don't need to break into the X and Y components of momentum. So I thought I'd just mention that. Yeah, that's where I was meant to start off with to begin with, but I just completely got sidetracks and went off on a tangent. So here we go. So that's like this is the exception, but not the rule. Right, so I'll go through the last one because we've got 4 minutes left. The discs continue to slide until the cord is fully extended. When this happens, both discs change their speed and direction. By considering the forces that act on the discs, explain why momentum in the system must be conserved. So let's go back to it. So this is like a level 2 concept. Momentum is only conserved if there's no external forces. In this case, the tension in the cord is an internal force. So there's only internal forces within the system, thus momentum of the system is conserved. So the system's velocity doesn't change, and that implies that speed or direction doesn't change. And I think there's one more, question D. What is question D? Oh no, that is really it. So it's 8:57. If you've got any questions, you can chuck them in the chat. If there's any like burning questions that you have. Otherwise, I think we might close it off. With any other questions? I don't think there are.
Nothing else in chat at the moment, Andrew.
No.
So
we'll give it a minute.
Very much for that. I'll just talk while we're waiting to see if any other ones pop in. Really like the calculator at the side. It's great to be able to see you do those calculations, and it's always a good reminder to carefully double check your calculations in the exam.
Yeah, one thing I probably didn't really go over. It's like, so when you're doing this in the exam, obviously you're not having to try and talk your way through it, but once you've done a question, have a good think about it. So have a think about the answer and think, is that the right way to do it? So that's what happened with question 3. What do we got? II. Determine the momentum of the disc after the collision. I just started like blasting through it just habitually without even really thinking about it, and I got about halfway through and I thought I had a good think about the question and went back up and I thought that's not right. I haven't been doing it from first principles. So first principles, I should have broken it down into its vectors, and then I should have worked from there. It's a really common thing just to try and blast, to whiz on through without like really thinking through each question and what the examiner is trying to ask. So also this was question BII. So this is an excellence question. So they're expecting you to have like 3 or 4 steps. So the steps were the vector component. So the whole idea of putting it into like a vector, making a picture out of it, using vectors to describe the system, and then from there picking up that you had to use Pythagoras, or you had to break it into 2 triangles, work out like either side, use Sokotoa, and then work from there. So that's about it.
Awesome. Thank you very much, Andrew. And we'll look forward to catching up with you tomorrow night for the waves and electricity papers.
Yep. So, yeah, see you then.
Awesome. Thank you. See ya.